Guys, my name is Aurash Daneshmayeh, and today I'm going to be reviewing a comparison of approaches to large-scale data analysis by multiple authors, and I name my presentation a comparative performance analysis of Hadoop, MapReduce, and parallel database systems for data-intensive tasks. What is the problem? The paper presents a detailed benchmarking study comparing the performance of MapReduce models, specifically Hadoop, with two parallel database systems referred to as DBMSX and Vertica for large-scale data analysis. The study aims to evaluate the trade-offs between these data analysis systems under various conditions. Yes, the problem is clearly stated, and the paper focuses on providing empirical evidence and a detailed analysis of the performance of the models compared to the parallel database system, highlighting various aspects such as data loading, execution time, and scalability. The author makes the important issues very clear. The paper delineates the performance bottlenecks and efficiency issues in Hadoop, particularly in comparison to parallel database systems. It discusses aspects like the speed of data loading, the efficiency of data querying, the overall scalability of the systems, which are crucial for understanding the practical implications of choosing one system over the other for data-intensive tasks. The important issues such as MR's execution strategy and how it handles data transfer between map and reduce jobs are made vividly clear. The paper delves into the architectural decisions of MR and DBMS and how these decisions affect their relative performance, specifically addressing the performance problems related to MR's handling of data transfer. Now, I've included figure 1 from the paper on this slide because it shows the load times for different data sets. It clearly illustrates the performance differences in data loading between Hadoop and parallel databases, which is basically what this project is diving a little deeper into. Now, why is this important? The problem is highly significant and relevant, particularly in the context of big data and data analytics. With the exponential growth of data, choosing the right data processing system is crucial for the business, researchers, and people using it. The performance of these systems directly impact the efficiency, the cost, the scalability of data processing operations, which is central to the numerous applications in today's data-driven world. There's a lot of reasons we should care about the problem, along with practical applications and real-world applications, as well as the paper's results showing why. So yes, there are several reasons to care about this problem. The first of which is going to be for decision-making, rather business decision-making. The insights from the paper can guide organizations in selecting appropriate systems for data processing, influencing decisions regarding the technology of infrastructure. Technological optimization, understanding the strengths and weaknesses of Hadoop and parallel databases can help in optimizing their use for specific types of tasks, leading to more efficient data processing. Industry standards and trends, the paper finds can influence industry trends in data processing, potentially leading to improvements and innovations in data processing technologies. And I know I said there's 3, but I have a 4th one for you guys. Educational and research implications. For students and educators and researchers in computer science, data analytics, and data science, the paper provides valuable empirical data for understanding the performance dynamics of popular data processing systems. While the problem of data processing itself is not new, the specific comparative analysis of Hadoop and parallel databases, especially in the manner presented in the paper, provides a nice fresh insight into the topic. The approach of using a range of benchmarks to test the various aspects of the system performance adds new dimensions to understanding these systems and context of contemporary data-intensive tasks. Here's a new question. Why is it challenging? Other than it looks crazy? The problem's difficulty lies primarily in its technical and computational complexity rather than being an issue of theoretical complexity like NP completeness. The key challenges include computational complex operations, which the task involved in the comparison, such as data loading, processing, querying, and computational intensive tasks. These operations demand significant resources, especially when dealing in large data sets. Next, we have large search space. The problem involves a large search space due to the vast variety of data-intensive tasks that can be performed and the numerous ways these tasks can be executed within each system. The system's performance can vary greatly depending on the nature of the task, the size of the data, the system configuration, and the underlying hardware. The next challenge we face is optimization across diverse scenarios. Optimizing data processing systems for a wide range of tasks is inherently challenging. Different systems have different strengths and weaknesses, and systems that excel in one type of task don't necessarily excel at another type of task. We have architectural differences, understanding and comparing the performance implications of architectural differences between Hadoop and parallel database systems. And to add to complexity, each system has its unique way of handling data storage, processing, and retrieval, which impacts its performance and scalability. And lastly, we have practical implementation challenges, implementing and fine-tuning these systems for optimal performance in real-world scenarios. which can be complex and time-consuming, but it involves understanding system-specific configurations, resource allocation, and the nature of data being processed. In summary, while the problem is not necessarily about theoretical computational complexity like NP completeness, it's challenging due to the practical complexities involved in handling, process, and optimizing performance for large data across different systems. Now, I've included two visuals here, figure 1 and 4, to demonstrate the challenges in data handling and processing across all systems. Now let's get into the meat of this thing and let's talk about some limitations. Previous works have explored the performance of data processing systems, but the paper presented a detailed head-to-head comparison of Hadoop, MapReduce, and parallel database systems using a comprehensive set of benchmarks. This level of detailed empirical comparison is less common than the prior works. No, this is not a trivial variation or extension of previous work. This paper provides a novel approach by conducting a thorough and comparative benchmarking across a range of tasks, which we'll get into later, and data sizes, offering new insight and performance differences between two types of systems. The paper demonstrates awareness of related work in the field of data processing systems. It builds upon the foundational understanding of Hadoop and parallel databases, but goes further to empirically test and compare these systems. Regarding the assumptions and limitations of related work, the authors discuss how system-level architectural designers influence the performance of data analysis systems. They highlight that the configuration parameters impact performance and that some limitations of previous work affect performance in fundamental ways. For example, they point out that MapReduce does not transform data upon loading, which precludes the I/O optimization necessities, runtime, and parsing, thereby increasing CPU costs, and other limitations are more specific to different implementations, such as high startup costs of MR systems. The author works builds on the foundation by providing empirical performance comparisons and by suggesting areas where MR and parallel DBMS architectures can learn from each other overall system performance. The paper discusses various limitations related to the systems being evaluated in the scope of the study itself, i.e. memory limitation. The paper mentions encountering memory limitation with the DMBX system. The default parameter for buffer pool size and stored heaps were found to be too conservative, and the system was ineffective in automatically adjusting memory allocations to changing conditions. Manually changing these configurations sometimes led to DMBX refusing to boot, indicating a limitation in the system's ability to adapt to user modifications. And another limitation that I want to bring up is handling of failures. While the paper notes that all database systems tested are tolerant of software failures, MR is particularly adept in minimizing work loss due to hard failures. However, this robustness against failures comes with performance penalty of the need to materialize immediate files between the map and reduce phases. The paper does not quantify the performance penalty, as it would require implementing both materialization and non-materialization strategies, common framework, which is beyond the scope of the study. Thank God. One way to critique his assumptions, the author seems that the performance penalties associated with the materialization of intermediate files in the MR are necessary trade-off for its robustness against hardware failures. While this assumption is reasonable, it's essential to consider whether this trade-off is always justified. In environments where hardware reliability is high, the performance penalty might outweigh the benefits of the MR's fault tolerance. Moreover, in use cases requiring maximum performance over fault tolerance, this assumption could be challenged. So what would the impact be of removing this assumption? If we were to remove this assumption that the performance penalty for fault tolerance is a necessary trade-off, we might encourage the development of more MR systems that do not materialize intermediate files or do so in a more optimized manner. This could lead to MR implementation that are both fault tolerant and have higher performance, potentially expanding their applicability in scenarios where parallel DMBSs would be preferred due to their superior performance. The impact of such an innovation could be significant, offering robust and efficient large-scale data analysis options that could challenge the current dominance of parallel DMBS in current sectors. All right, I told you guys this part was going to get dense. We got this slide and two more to get through, so I'll get through it for you guys. The paper makes several key contributions to the field of data analysis, particularly in the context of comparing the MapReduce model with the database management systems. A comparative analysis of MR and parallel DMBS. The paper provides a comprehensive comparison between the MR model, particular Hadoop, and two parallel DMBS systems. The comparison covers performance and development complexity aspects. Development of bench trademarks, which was pretty unique to this paper. The author developed a benchmark comprising 5 tasks, one from the original MR paper, and 4 additional complex analytical tasks. This benchmark is specifically designed to explore the performance trade-offs between the MR model and the parallel DMBS. I'd also like to highlight empirical evaluations on a large cluster. The benchmarks were run on a cluster of 100 nodes, measuring the performance of each system under different degrees of parallelism. The empirical evaluation provides practical insights into the scalability and efficiency of these systems. Let's talk about extension of some related work. The paper builds upon a previous work of the MR model and parallel DMBS, providing a direct empirical comparison of these approaches in large-scale setting. The problem can be seen as an extension of related work in the field of data processing. While previous studies have individually analyzed the performance of Hadoop and parallel databases, this paper extends by conducting a head-to-head comparison when using a set of comprehensive benchmarks. While the basic control flow of MR has been part of the parallel SQL DMBS for over 2 decades, this paper explores the claim of MR being a new computing model, comparing it with parallel database system. This is not a new problem. The core problem of comparing large-scale data analysis approaches isn't new, but the paper addresses it in a novel context by bringing a fresh perspective by empirically evaluating the MR model against modern parallel DMBSs, which is relatively less explored area. In regards to proposed approaches, algorithms, and idea, the paper does not propose a new algorithm or systems, but focuses on evaluating existing ones, Hadoop, DMBS, and Vertica, under a set of benchmark tasks. The idea is to assess how these systems perform in the real world like scenarios and what trade-offs they have. Now let's dive into a little analytical evaluation. This is going to get a little deep, so bear with me. The analytical evaluation is centered on comparing the performance and development complexity of MapReduce and parallel DMBS. The findings show while parallel DMBSs took longer to load data and tune for execution, the performance was significantly better compared to the MR system. The paper then goes on to speculate on the cause behind the performance differences and suggests implementation concepts for future systems that combine the strengths of both architectures. The study includes a detailed analysis of the performance results, discussing factors like system configuration and data loading times, as well as performance of different tasks under varied conditions. Now let's dive into the statements that they use, and let's start with the task execution, the grep task. SQL commands. Basically, a task involved a full table scan in both SQL systems, as there was no index on the search field. The MapReduce program involved a single map function to perform a substring match. Results: the performance differed significantly between the two types of tasks. For tasks involving less data, specifically 535 MB per node, the startup cost of Hadoop became a limiting factor. In tasks with more data, 1 terabyte or more a cluster, Hadoop's startup cost was overshadowed by the actual processing time. Hadoop and DMBSX performed similarly due to the amortized startup cost over increased data processing. Vertica outperformed both Hadoop and DMBX, attributed to its effectiveness of data compression. Next, we're going to be on to the selection task. This is probably the last big one of this paper, so I'm happy for you guys. So let's start. The SQL command was a simple SQL query, was used for the selection task. MapReduce program implemented with a single map function to process and output records based on the threshold. Let's talk about these results. Parallel database management systems, Vertica and DMBX, significantly outproduced Hadoop across all cluster scaling levels. The relative performance of all systems decreased with increasing nodes and data volume, but Hadoop was most affected due to its increased startup cost again. The efficiency of parallel database management systems was partly due to their use of indexing and pre-sorted data, making query execution trivial. Despite Vertica's low absolute times, its relative performance degraded with more nodes, likely due to the overhead in its messaging layer. I've included figure 4 in this table because it illustrates the results of the grep task with a data set of 535 MB per node. It provides a visual representation of the performance comparison between Hadoop and Vertica across the different cluster sizes. This figure is particularly informative as it demonstrates the performance differences between the two systems under specific tasks and highlight how Hadoop's startup costs become a limiting factor in its performance when processing smaller data sets. These results provide a new view of performance characteristics of Hadoop compared to parallel database management systems. They highlight the importance of factors like startup cost, data compression, the efficiency of indexing, and determining the overall performance of data analysis in large-scale environments. The study is finding out also MapReduce frameworks like Hadoop and other flexibility scalabilities. They may be less efficient than parallel database management systems for certain tasks, especially those involving data processing or requiring efficient query capabilities. Guys, bear with me, we're almost through this thing. Start talking about the case studies. The benchmark consisted of 5 tasks, including of 1 simple from original MR paper and 4 additional complex analytical workloads. This allows for the detailed case study of how different systems perform under various data analysis tasks. Finding from the studies basically centered around performance variability, that these systems varied significantly depending on the type of task suitability. Some tasks were better suited for the MR model, while others showed up superior with the parallel DMBS systems. System configuration and optimization. The study also revealed how different configurations and optimizations could be affected by system performance. For example, changes in data block size in Hadoop or enabling compression in DMBX significantly influence execution times. And we went over scalability, which showed how each system responds in the data volume and computational resources, data loading and processing times taken for data loading and processing was measured for each system. These metrics are crucial in real-world applications. Both in preparation and analysis phase are both time sensitive. What was the purpose of even including a case study? Empirical evaluation to provide a real-world evaluation of how these systems perform under different conditions and workloads, and which is better for what. It also offered guidance for system selection, giving insights that help in deciding which systems to use for which specific task of data analysis. And the underlying trade-off to understand between MapReduce framework and like Hadoop and parallel DMBSs in terms of performance, scalability, and suitability for different kinds of data processing tasks. Now, the computational complexity, we don't explicitly analyze that in this paper. In theoretical terms, it does assess the performance implications of different systems and configurations and data processing tasks. And lastly, let's get to the validation methodology. We had tested systems of Hadoop, DMBSX, and Vertica. Hadoop is an open source implementation of the MR framework. DMBSX is a parallel SQL DMBS from a major relational database vendor. And Vertica is a parallel DMBS designed for large data warehouses. Now on to our benchmark execution. Each benchmark task was executed 3 times on each system, and the average performance was reported. The tasks were designed to ensure exclusive access to the cluster resources that were executed on varying cluster sizes to access scalability. The study also accounts for the time taken to load the data into each system. Now, what are the strengths and what are the weaknesses? Let's get to the core of this thing. The strengths were the comprehensive testing, which included a variety of tasks to test the system under different scenarios. We had a uniform environment. By maintaining a consistent testing environment across systems, the study ensured that the performance differences observed were due to the systems themselves and not external factors, adding validity to the study. And it's repeatable. The methodology is detailed enough for anyone to follow and recreate. Now, the weaknesses were limited to specific configurations. The study's findings might not generalize to other configurations or versions of the system. And there's a potential bias in task selection here. The chosen task may favor certain system strengths over another. We're not really sure why those were chosen. The author likely chose these methodologies to provide a fair and comprehensive comparison of the MR model against established parallel database management systems. The benchmark tasks were selected to cover a range of operations, typically into large-scale data analysis, allowing for a thorough evaluation of each system's capabilities and limitations under different conditions. I included figure 7 in this slide because it illustrates the performance differences in a task that involves aggregating a large number of groups, showcasing how the runtime of each system is affected by factors like the amount of data, the number of nodes, and clustering, providing a deeper understanding of scalability and efficiency of each system, and handling complex aggregation tasks, which is a crucial aspect of the study's methodology. And I'm pleased to announce that this is the conclusion of my presentation. In essence, the paper concludes that while parallel database systems have a clear performance and efficiency edge over the Hadoop MapReduce, the latter's ease of use and fault tolerance for significant benefits. They also recognize that the field is evolving with improvements expected on both sides that could change the landscape of large-scale data processing in the future. I included some future work that could build off this study and maybe take it to the next level. We could look into fault tolerance in parallel database systems, investigating methods to enhance the fault tolerance capabilities of parallel database management systems without significantly impacting the performance. Could be another thing that's interesting. Or we have the optimization of MapReduce. Given the performance penalties highlighted for MapReduce, future research could focus on optimizing its execution model to reduce startup overhead and improve the data handling efficiencies and honestly just lower its CPU intensity. Thank you guys for listening. I hope you learned a little something in this presentation today.